Gentlemen, good morning. Let's continue with chapter 7 from the textbook of Cengel and Ghajar. Chapter 7 is on external forced convection. External means on the outside of bodies, and with the previous lecture I've identified quite a number of bodies that we are interested in, and they were covered in paragraph 7.1. So in this chapter, we've got paragraph 7.1, which is the drag and heat transfer in external flow, and then parallel flow over flat plates. And with the previous lecture, we just quickly revised your fluid mechanics part, which are about the skin friction coefficients, the average coefficient, the average drag coefficient of a flat plate. But then we've also introduced the Nusselt numbers, which takes into consideration the heat transfer. So anything like this, CFX or the Reynolds X, means it's the local value at a specific point. We as engineers do not want to go and calculate it at 10 or 20 or 100 points over a flat plate and then do the integration. We would preferably want to work with one value, and this would then be the one value, the average value over the length of the plate. That is why it is the Reynolds number based on the length of the plate. And correspondingly, we can go and determine the local Nusselt numbers and the average Nusselt numbers. Again, for laminar flow, which means the critical Reynolds number is less than 500,000. If the flow is turbulent, then we've got another set of equations, again for the skin friction drag, as well as the heat transfer. In this case, all the flow is considered as laminar. In this case, all the flow is considered as turbulent. Now, there cannot be a flat plate case without laminar flow, because at the leading edge, the Reynolds number is 0. So already you cannot get there, and just by moving on 0.5 of a millimeters, there the Reynolds number will exist. It will be a small value, and you will always have a first part which is laminar. But there are some practical cases, if you look at the entire body, that the laminar part would be negligible. And in general, you can say, all the flow is turbulent. Then you can use this equation. Otherwise, if you want to be safe and you want to take into consideration the laminar part, then you can do it with this equation for the skin friction drag as well as the Nusselt number. So it is just a quick summary of what we've done with the previous lecture. Then, this is not the end. You will also see in the textbook there's actually a part where a plate is being considered, where the first part is a part in which there's no heat transfer, and then in this part heat transfer will start, so there will be an unheated part with a difference of distance of eta. And then you can also go and derive some analytical equations for that. You can just take note of it. We are not really going to make use of it in our work. So what I would like to do now is I would like to show you 3 possible scenarios of only laminar flow and then only turbulent flow, or where we make the assumption that everything is turbulent on the plate. It cannot be, it never is, because there's always a laminar part. And then we're going to have a third scenario where we have to take into consideration the laminar part of the plate. Now, this example consists out of a flat plate with a width of 1 meters and a length of 5 meters. And we have oil at a temperature of 60 degrees Celsius and 2 meters per second flowing over this plate, and the surface of this plate is at 20 degrees C. It is maintained at 20 degrees Celsius. And we would like to determine two things. We would like to know what is the drag on the plate, and secondly, what is the heat transfer rate over the plate. So if the oil is at 60 and the surface is at 20, then it means there will be a heat transfer from the oil to the plate, and that would be the heat transfer. Right. So the width is 1 meter, the length is 5 meters. Oil at the temperature of 60 degrees Celsius flows at a velocity of 2 meters per second over this flat plate at a temperature of 20 degrees Celsius. As we've discussed with the previous lecture, we always need, as you can see, the Reynolds numbers and the Prandtl numbers. But the Reynolds numbers and Prandtl numbers need to be determined at a certain temperature, because the properties, the densities, the CPs, and the viscosities are all a function of temperature. How do we do it? Well, we calculate a film temperature, and we are going to say in this case the film temperature is equal to the temperature of the surface plus the temperature of the oil divided by 2. The temperature of the surface is 20, the oil is at 60 divided by 2, so we would like to know the properties at the temperature of 40 degrees Celsius. And if you would be so kind, and you've got your textbook here, I want you to go and look in table A13 for the oil properties, and please give it to me quickly. So please take a minute, go to your textbook. There's a lesson to be learned in what I'm going to show you now. And this lesson you should of course not repeat in the test and exam, because then it's going to cost you quite a number of marks. So in table A13, at a temperature of 40 degrees Celsius, please go and get the properties for me. While you're busy, I'm going to write it down. Density is equal to 876 kilograms per cubic meter. The thermal conductivity K is equal to 0.1444 watts per meter Kelvin. Ladies and gentlemen, if you've got your textbook here, please please open it, because most probably you would like to write a very important note in it. That's the K value. The Prandtl number is equal to 2.962, and the kinematic viscosity is equal to 2.485 multiplied by 10 to the minus 4 square meters per second. Do you all agree? Do you get those properties for the oil? You're all wrong. Why? I think you know.
So is it because we took our film temperature is incorrect? Isn't it, we're looking for the properties of oil?
Yes, properties of oil.
The count of the surface.
Okay. Now, what we do in principle is the temperature is fine. We will always take the average temperature. There will actually be problems where maybe one of the two is unknown. What you then can do is you start with a known one that you have. You're going to use those properties, you're going to work through, you're going to determine the surface, and then you can again get a revised film temperature, and you can get revised properties. Normally you do not need to iterate it more than 2 times. Normally very quickly where you will have convergence. Okay. The thing that you need to be careful for is that in American textbooks, they use a comma there. So it is not 2.962, it is 2,962. Okay. So you need to make a note in your textbook that the comma that you see there is 1,000. It's not 2 point or 2 comma something, it is 1,000. Do you see that? And that is not the only table where you're going to get it. There are a few other places in those tables where there's the same nomenclature which is being used. So please be careful for that. Let's start by calculating the Reynolds number over the length L. The Reynolds number here at the leading edge will be 0, and it will increase in this direction. So the maximum Reynolds number is here at the end of the plate. We call it Reynolds over the length L, would be equal to the velocity multiplied by the length of the plate divided by the viscosity. The kinematic viscosity, like that, which is then equal to the velocity, which is 2 meters per second, the length is 5, and the kinematic viscosity is 2.485 multiplied by 10 to the minus 4, and that gives us a Reynolds number of 4.024 multiplied by 10 to the 4th. If we look at this Reynolds number, this is about 40,000. Well, it will only be turbulent if the critical Reynolds number is 500,000. So we can make the conclusion that this flow is laminar everywhere over the plate. There is no transition. Do you understand that? Okay. Also, something that you need to look at is we've written the Reynolds number like that. We could have also written it as rho VL divided by the kinematic viscosity or the dynamic viscosity. You can also get the dynamic viscosity and work with that. You can see the advantage. By using that one, you can just work with a one term, VL divided by the kinematic viscosity. So it's very simple. Right, now we know the Reynolds number, and if we know the Reynolds number, we know that these equations are valid, so that would give us the average drag over the entire length of the plate. So the average drag coefficient is equal to 1.33 divided by the Reynolds to a half, 1.33 divided by the Reynolds is 4.024 multiplied by 10 to the 4th to the half. And if we calculate the drag coefficient, it will be equal to 0.00663. Okay? If we've got the drag coefficient, it is just one more step to get the drag. The total drag would be equal to the drag coefficient multiplied by the surface area multiplied by rho v squared divided by 2. The drag coefficient is equal to 0.00663. We've determined it just now. The density is equal to 876 multiplied by the velocity, which is 2 squared, 2 meters per second divided by 2, and it gives us a drag force of 58.1 newtons. Okay? Simple. We've done that in fluid mechanics. sorry, I didn't use the area. Okay. The area, of course, is 1 by 5. 1 multiplied by 5. Yes, I have to include the surface area, thank you. Therefore, it's 58.1 Newton. It's a small drag force. Let's determine the heat transfer. For that, we first need to get the Nusselt number. Again, we're going to use the Nusselt number for laminar flow because everything is laminar. It's equal to 0.664 multiplied by Reynolds out to the 0.5, Prandtl to the third. Equal to 0.664. The Reynolds number 4,02 multiplied by 10 to the fourth, 0.5. Prandtl is 2962 to the third is equal to 1913. Nusselt number of 1913. The Nusselt number, by definition, is equal to the heat transfer coefficient multiplied by the characteristic length divided by the thermal conductivity K. The Nusselt number we have determined as 1913 is equal to the heat transfer coefficient multiplied by the length of the plate, which is 5 meters, divided by the thermal conductivity K, which is equal to 0.1444, from which we can solve that the heat transfer coefficient is equal to 55.25 watts per square meter, degrees Celsius. Once we've got the heat transfer coefficient, we can calculate the heat transfer rate. The heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area, the temperature of the oil minus the temperature of the surface. I choose the highest temperature first. You don't have to be as strict as in thermodynamics to indicate the direction of the heat transfer. It's logical. So the heat transfer rate is equal to the heat transfer coefficient we have solved as 55.25. This time I'll remember the surface area, which is 1 multiplied by 5. Temperature difference, the oil is at 60, minus the plate temperature, which is 20, and that will give us 11,150 watts. Okay, that's not an engineering answer. The answer is 11.1 kilowatts. Do you all agree? Just remember that what we've looked at in this case is the heat transfer only from the one side. If this was a plate that was in the air and it was heated and maintained at 20, then we also have to take into consideration the heat transfer from the bottom side of the plate. This is just from the one side. Any questions? Do you all understand it? Very simple. We go and check the Reynolds number. If it indicates the flow is laminar up to the leading edge, or the trailing edge, then it means everything must be laminar. For laminar flow, then we can make those assumptions, those equations, and we can use that. Okay? Now let's do the opposite problem. And in this problem, we are going to look at a house or a building. There it is, and the length of this wall is 50 meters, and this height is 4 meters. The length of the wall is 50 meters, and the height is 4 meters. And there's a wind blowing at a velocity of 7 kilometers per hour, and it's a cold wind, and its temperature is at 5 degrees Celsius. And the surface temperature of the wall is at 12 degrees Celsius. Now that would be a typical temperature if the room on the inside is being maintained at a temperature of 20 degrees Celsius. So again, the question is, what would the drag be on this wall, and what would be the heat transfer rate from that one wall? So we only look at this surface. The surface with a length of 50 meters and the height of 4 meters. Again, the thing about the properties, it is dependent on temperature. Which temperature? Well, we've got 12 degrees and we've got 5, so we are going to use the film temperature, which is the surface temperature plus the wind temperature divided by 2, and that is 12 plus 5 divided by 2, that's at 8.5 degrees Celsius. In the previous problem, we've looked at the properties for oil, and now we want the properties for air. So you need to go to the necessary table for air, and at the temperature of 8.5, and there you will find that the thermal conductivity K is equal to 0.02428 watts per meter degree Celsius. The kinematic viscosity is equal to 1.413 multiplied by 10 to the minus 5 square meters per second, and the Prandtl number is equal to 0.7340. There's all the properties. And the first question that we need to ask is the flow laminar or turbulent at the end? We know that the Reynolds number there is 0, so there should be a laminar part, but in general, by the time it is to the end, is the flow laminar or turbulent? Question?
There was a restriction for the laminar flow that said the Prandtl number was more than 0.6. Is it the same for the laminar?
Yes, every one of those equations have a limitation in terms of the Prandtl number, the Reynolds numbers, etc. It's the fine print, and I'm going to refer a lot to the fine print, that you always have to go and check the fine print. I didn't write the conditions here, but I'm quite sure that we met with it. Okay, so if I remember correctly, typically many of the derivations has been done with a Prandtl number of 1. It makes things so much easier. And then they've tested it experimentally for other Prandtl numbers, and normally specific most gases, their Prandtl numbers go down to about 0.6, air also about 0.6. So in general, most of the gases are also fine with the equations. It's just when you start getting to things like liquid metals, mercury, for example, then you've got normally another set of equations that you need to use specifically for them. Right, now, so let's go and check the Reynolds number, and we calculate the Reynolds number here at the end of the plate. It's equal to the velocity, the length, divided by the kinematic viscosity. The velocity in this case is 7 kilometers per hour, divided by 3,600. 7, it's a kilometer, it's 1,000, an hour, 3,600 seconds, and that is how you get the velocity in meters per second. Is that clear to everybody? Okay. Multiplied by the length, and in this case the length is quite long. It's 50 meters, divided by the kinematic viscosity 1.413, multiplied by 10 to the minus 5, and that would give us a Reynolds number of 6.88 multiplied by 10 to the 6. Okay. If we look at this Reynolds number and the critical Reynolds number, which is 5 multiplied by 10 to the 5, it is clear that the flow is turbulent. Okay? But the question is, if this is now the plate, like that, or the wall, which is 4 meters by 50 meters, here the Reynolds number is equal to 0. Here at 50, it is 6.88 multiplied by 10 to the 6. So the question is, where will the flow changes from laminar to turbulent? And it will change at the critical Reynolds number of 5 multiplied by 10 to the 5. So what we can do is we can go and calculate where that is by using the critical Reynolds number. So we can say the critical Reynolds number is equal to the velocity multiplied by xcr, the critical length, divided by the kinematic viscosity. We want to know at 500,000, 5 multiplied by 10 to the 5 is equal to the velocity of 7 kilometers per hour. And now we calculate xcr divided by the kinematic viscosity, which is 1.413 multiplied by 10 to the minus 5. And from this, we can calculate that the critical distance, or the critical length, is equal to 3.6 meters. 3.6 meters. Okay. So if we look at it in perspective, that is the wall of 4 meters by 50. Okay. So that's 50 meters, that is 0. 3 meters is about approximately there. It's less than 10%. It's 50 meters, 5 meters would be 10%. So we're talking of about 3%, just 3% of the plate would be laminar, 3.6. Okay. So there it's going to be laminar, but the rest of the flow would all be turbulent. So, as engineers, we will look at it and say, in general, the majority of the flow field is turbulent. And I don't know if you're as lazy as I am. I don't want to go and do lots of calculations. If I can use an easier equation, I prefer to use the easier equation. And that is what we're going to do. So we're going to assume all is turbulent. It is not true, can never be true, but the laminar part is small in comparison with the rest of the length. Right, so now we're going to calculate the drag coefficient, and now we use it for turbulent flow. Okay, take note. So now we're going to go for the turbulent part. There's the laminar part. Here's the turbulent equations. There's the one we're going to use for the drag, and that is the one we're going to use for the heat transfer. So CF is equal to 0.074 divided by the Reynolds number based on the length to the fifth, which is equal to 0.003175. From this, we can calculate the drag. The drag is equal to the drag coefficient multiplied by the surface area multiplied by rho v squared divided by 2. The drag coefficient is equal to 0.00317 multiplied by the surface area, which in this case is 4 meters multiplied by 50, multiplied by the density, I think I've missed putting the density here of air. It should be approximately 1. So you can just go and refine it, multiplied by the velocity, which is 7,000 divided by 3,600 divided by 2 to the power of 2 divided by 2, and that yeah, okay, that's right, it's 1.5 Newton. So it's very small, the drag force. Okay? Now we've got the drag force. Now we want to calculate the heat transfer. For that, we have to determine the Nusselt number is equal to 0.037. Reynolds based on the length multiplied by Prandtl to the third. That would be to the 0.8. I'm not going to put in all the values, they are all there, so you can just go and calculate it. It will give us a Nusselt number of 9,852. This Nusselt number is equal to the heat transfer coefficient multiplied by the length divided by the thermal conductivity K. The Nusselt number is 9,852 is equal to the heat transfer coefficient multiplied by the length, which is 50, divided by the thermal conductivity is 0.02482. It will give us a heat transfer coefficient of 4.784 watts per square meter degrees Celsius. So the heat transfer coefficient is equal to the heat transfer rate is equal to the heat transfer coefficient multiplied by the area multiplied by the temperature difference, temperature of the surface minus that of the wind. In this case, I write the temperature of the surface, which is 12 degrees first, in comparison with that of the wind, which is 5. And then we can go and calculate the heat transfer rate, which is equal to 4.784 multiplied by the area, which is 50 multiplied by 4. And the temperature difference is 12 minus 5. And the result is a heat transfer rate of 8,698 watt, which is about 8.7 kilowatts. 8.7 kilowatts of heat transfer. Take note, we have not taken a radiation heat transfer into consideration. And this is, of course, now for one wall only. About 8.7 kilowatts, almost 9 kilowatts of heat transfer through this wall. For those of you who are interested in air conditioning and ventilation of buildings, if you look at this building, then you would immediately realize that most probably you're going to have the same heat transfer in the other direction. You're going to have a similar heat transfer rate through the roof, and of course through that wall and that wall. You can go and calculate everything. If I just look at that, I will be surprised if you would not need if you would need less than about 40 kilowatts for the heating of that building to maintain it at a temperature of 20 degrees Celsius when you've got that cold wind of 7 kilometers per hour blowing over it for a long period of time. Any questions, ladies and gentlemen? Yep.
So is there a rule of thumb for how much of the section can be laminar?
No. Is there a rule of thumb for how much can be laminar? I would say no. You will later on see that in heat transfer, lots of the correlations are empirical. They have been determined from experiments. Many of the experiments were done years and years ago when the instrumentation wasn't so accurate and when the method of determining the uncertainties were unknown. So most of the heat transfer equations are plus or minus 20%. Okay, very, very few has accuracies of 10% and even low. So in general, this depends on the situation. There are many, many cases in industry where you want to make a back of an envelope calculation. Okay? And then I'm quite sure 10 or 20% would be fine. However, if you are competing against another company where the specifications said that we want to maintain the temperature at 20 degrees Celsius, then what's going to give you the competitive edge against somebody else making a rough calculation is that when you've got confidence in your own calculations, and then you're really going to take that small area into consideration, because most probably you're going to end up with maybe a tender price smaller than him, and or he or she is going to install something that is not going to make the specification. So it depends on the situation, if it is rough first order calculations, and or if you are in competition against other people. I think I hope that answers your question. Okay. Right, now the third scenario. Yeah, another question.
Why don't you consider transition as that?
Yes, why don't we consider transition? Transition up to recently has been considered as an area where engineers should stay away from. It was very unpredictable, lots of fluctuations, etc., etc. However, in the past 10, 15, 20 years, a group from Oklahoma State University, Professor Cengel and Ghajar, and also our group at the University of Pretoria has made lots of new contributions in that regard that actually shows that you can quantify it very, very well and you can take it into consideration. Okay. But in general, it is easier, less work if you stay away from it. So you just make the assumption that the transition is only at one point, and this is laminar, and that part is turbulent. But you're right. In many cases, your transition part is that area. And again, it now depends if you really want to compete against your competitors and or if you want to make a rough calculation. If you want to compete against your competitors, you can actually take that into consideration. There's actually no work yet for a flat plate in terms of determining really the transition characteristics. However, we have done a lot of work for smooth tubes. So if you want to have the transition characteristics for smooth tubes and or spiraled fin tubes, that has been done and that has been published, and you can actually go and determine that from the correlations which are available. Okay. Any other questions? Right, let's do the third example. Okay. Now this, again, is this building. And now that length is 5 meters and that is 4 meters. The surface temperature is at 12 degrees Celsius. The air is at 5 degrees Celsius on the outside, and the wind is 10 kilometers per hour. Okay, so our surface in this case is 5 by 4 meters. So much shorter than that of the previous example. And I'm going to skip some of the detail. I'm just going to give you the most important results so that you can go and do it at home, because there's not going to be enough time to write out all the detail. But what we can do again is we can go and determine the film temperature. The film temperature is going to be the average of the two temperatures of the 12 and the 5 at 8.5 degrees Celsius. Air properties are given in table A15, and there you can go and get all the properties for K, the kinematic viscosity and the Prandtl number, etc. Please go and do it at home. You can go and determine the Reynolds number. So the Reynolds number would be now at the end of the wall, which is 5 meters. Is equal to VL divided by the kinematic viscosity. The velocity is 10 kilometers, 10,000, divided by an hour, 3,600 seconds. Now the characteristic length is 5 meters, divided by the kinematic viscosity, 1.413 minus 10 to the minus 5, and the Reynolds number is 982,936. Okay. Therefore, it's turbulent. But again, just as in the previous case, it would start off as laminar, and then it's going to change to turbulent, somewhere along the length. Where? Well, we do exactly the same thing. We say, we know the transition will occur at 500,000, is equal to the velocity multiplied by the length. In this case, I've used L critical. You can also use X critical, just as you want. Divided by the kinematic viscosity, 500,000. You can go and put in all the values. You want to get the critical length, and the critical length is, as previously, about 2 to 3 meters, 2.5 meters. Okay, 2.5 meters. So, if we look at the problem in perspective, that is x equals 0, and that is x equals 5, 2.5 meters is approximately here. Okay. So it's about 50% of the length is going to be laminar. So that flow there is going to be laminar, and that flow is going to be turbulent. Different. So, going back to the possibilities that we have. Is all the flow laminar? The answer is no. Is everything turbulent? Only 50%. Therefore, let's rather use the longer equation where we have to take into consideration the laminar part. That is what that equation is there for. So you're going to use CF is equal to 0.074 divided by the Reynolds length to the fifth minus 1742 divided by Reynolds L. You can go and calculate it as 0.002913. And from that you can determine the drag force. It's very small, 0.21 281 newtons, it's almost nothing. Similarly, we can go and get the average Nusselt number, which is equal to 0.037, Reynolds L to the 0.8, minus 871, Prandtl to the third. Can go through all the calculations. That's going to give us a Nusselt number of 1,291. From the Nusselt number, we can go and determine the heat transfer coefficient, 10.09 watts per square meter degree Celsius. From the heat transfer coefficient, we can go and determine the heat transfer rate, which is going to be 1.4 kilowatts. 1,412 watts. I hope these three examples clarified everything to you in terms of how to use all those calculations. Thank you, ladies and gentlemen.